Hey everyone, it's Justin again. In the last video, you learned how to write exponential functions that perfectly match given data points. Here's the problem though. In real life, data usually doesn't fit perfectly on a function. In this video, you'll learn how to use technology to write functions that approximate data using a function known as regression. At the end of this lesson, you will be able to use the regression feature on a graphing calculator to calculate functions that approximate given data. To teach you this skill, first I'll give you a quick tutorial on how to perform both exponential and linear regressions, and then you'll have a chance to try it yourself with a practice example. We can agree that this graphed data set has a distinctly exponential shape, right? Cool. So let's find the function. The initial value is 10. And if we divide the next point by that, we get a growth factor of 6 over 5. The function will be 10 times 6 fifths to the x power, which looks like, this? Well, that's not right. It doesn't go through all the points. But if we change that initial value, it won't go through point A anymore. And if we alter the growth factor, it'll grow at a different speed and it won't pass through point B. The problem here is that we assumed these points were on a perfect exponential curve with a definite function, rather than the data being approximately exponential. There actually isn't a function that will pass through all of these points. But we can use technology to create a function that approximates the data as perfectly as possible, using a technique called regression. There are all different types of regression, and since we use it to approximate data with an exponential growth function, this would be called exponential growth regression. Most graphing calculators have the capability to do some forms of regression, but each calculator is different. So, for the sake of this demonstration, we'll be using a graphing calculator that everybody has access to. Interactive, free online graphing calculator from Algebra. Take a moment to open up this website in another tab. Here's the data from our first example. Pause the video while you type this data in on your own screen. The points you entered have already been graphed. We're just too zoomed in to see them. So let's change the viewing window. Our x values are from 0 to 6. So let's set the x from -2 to 10 just to give ourselves some extra room. And since the y values are between 10 and 96, we'll set that range as -10 to 110. Now we can see all of our data points with an obvious exponential growth curve. Since this data looks like an exponential growth function, we're going to use exponential growth regression. And doing that is simple. First, let's put all of our points in a single list. This will make it so that anytime we need to use all these points, we only have to tell the calculator what list to use. Now we can see all of our points are in this single list, L1. The next step is really easy. We want to use regression to find the curve of best fit. So we type fit. Look at all those different options that pop up. Remember when I said there are different types of regression? Algebra is showing us what commands to use for these different types. But be careful here. You can see the one called fit exp, but that's not the one we want to use for exponential growth. Instead, we want fit growth. Now it wants to know what points to use. We could type the names of all of our points, or we could just give it our L1 list, which already has all the points. And look, not only did it immediately graph the curve of best fit, it also gave us the equation. The line of best fit is 8.9520906866797 times 1.491647228864 to the xth power. We could round those numbers a little bit, but rounding is generally a bad idea here. As it stands, those are probably irrational numbers that have already been rounded automatically. So we want to keep them as they are instead of rounding any further. You can actually use the fit growth command for both exponential growth and decay, since they have the same basic formula. We can also perform other types of regression. Let's hide the exponential curve for a second and say, hey, that might just be a line. If it is a line, then we should use linear regression on it instead. Just like before, we'll use the best fit feature. But instead of fit growth, we're going to choose fit line and give it our L1 list. Just like with the exponential growth regression, it immediately graphed the line of best fit and gave us the equation of the line. So then the big question is the exponential regression or linear regression better? That's what the r² command is for. So type in the list of data, which is L1, and the function we're checking, which is the fit growth function, f of x. Then we're going to do that same thing again, but this time we'll use the fit line function, or g. R² is a measure of how close to the data the regression is. A 0 means that the line or curve doesn't fit the data at all, and you shouldn't use that regression. While a 1 means the line or curve fits the data perfectly. In fact, if r² is 1, that means you didn't even need regression. You could have found the function yourself. But most r² fall somewhere in between. For instance, our exponential growth regression had an r² value of about 0.9954, which is really close to 1, while the linear regression's r² was at 0.9091, which is a lot lower. What this means is that the exponential growth regression fit the data much better. If we want to approximate this data using a function, we should use the exponential growth regression, not the linear. I've thrown a lot of information at you, so let's put it all to use. Here's a set of data. Pause the video now and use GeoGebra to find the line or curve of best fit. First, we create the list L1 with all of our points in it. Now we can perform an exponential growth regression. And a linear regression. But which one is best? Well, we can find that out by doing an r² test on both regressions. They're close, but the linear regression's r² is a little closer to 1, so that's the winner. The line of best fit for this data is 9.85x plus 57.266 repeating. So how'd you do? If you need more practice, there are plenty of examples to practice with on our website. Now that you understand exponential functions and regression, you've completed the unit on exponential growth and decay. In the next unit, we're going to do something you've probably never thought of: multiplying algebraic expressions together. See you then.